পড়ানো আছে, ঠিক আছে রাখছি। হুম, দেয়া হয়ে গেছে। বাইরে। Hello Abhishek.
Uh, Hello, Nirvan. Uh, so, Nirvan, actually, I wanted to ask, like, according to our previous conversation, like, which we had last week, like, is there any update on the format of the question paper,
Yeah.
like whether
So
questions are going to come or not? Yeah.
I have updated that in the thread. So it is
Okay.
like the coding questions are mostly will not be there. Okay, but
Okay.
some might be there just to understand whether you have basic knowledge of the PyTorch library, which is used to code machine learning. Okay, just the basic thing, and that will be there. One or two question, not more than that. No,
Uh,
no,
so,
no VA type question, no diffusion type question. Yeah.
so, like, I just wanted to confirm one more thing. Like, I was looking at the assignment. So, approximately 50% of the assignments are of this type only, where we have to code out and then tell the output. So, it means that they are not that important. We should focus on rest of the 50%.
Yeah, but as you can understand, like mm, I mean, the rest of the questions might be like may not cover every topic, as you can understand. Means like some of the topics were covered with the coding questions, right? So, uh, and some were covered using the using theoretical questions. Okay, so the topics that were covered using coding questions, theoretical questions might come from them as well. Okay, means like you understand, right? If most of the question in our practice was from coding, but so the theoretical questions might not cover the full syllabus. You understand that, right? Yeah.
Okay, so got it. And one more thing I wanted to ask, like the non-graded assignments are also there. Do we supposed to do them also?
I mean, for practice, yeah. Uh, I do cover some of the questions here. Yeah.
Okay.
So, so the course is really tough. I can understand, and even like even if I would have taken it, uh, my understanding would not have been 90%. It is like 60-70%, something like that. Okay, so it is a tough course, yeah, but let's try to learn. Okay, so so I previous class I covered basics of the diffusion model. Okay, DDPM, mostly DDPM paper. So, but we'll need to, I think, go a little deeper into it. So that's the plan today. Okay, there's also extra session which I had booked. Let's say on which day. Uh, extra session. So there will be extra session. I just don't remember the date. Or let's find out. So there I will cover the week 12 actually. But I need to find that extra session. Which date did I book it? Mm, uh,
Anirban, can we get some previous year papers if possible?
Yeah, I've asked the admin of the NPTL. They are the authority to release them. So as soon as they do, I will release them. Okay. I don't have it personally.
Okay.
Uh, so there will be extra session. Just I when did I book it? Is the question. Uh, oh, okay. So there will be a session. I just cannot find the. Can you let us know the final exam pattern? Mostly will be understanding based. Will test your understanding. Okay, and so let's cover more into diffusion models today. Okay. So I'm presenting, no? So I'll present from there. Just wait a minute. Hard to remember the passwords. Uh, okay. So you can see the screen, right? And now I okay. Uh, so how much did you learn in diffusion models? Is the thing to understand. It's not a easy thing. DDPM. The coding assignments can come in the form of theory. Uh, yeah, means like the well, professor will try to cover the full course, of course. Understanding, test the understanding of the full course. So that's the cue to think about. Okay. So this is the paper. Okay. So so is there any doubt to take up on this first of all? Any confusion? I mean, the diffusion cannot be so easy that you have got it all covered. It was a challenging topic all the time. Any doubt? Anybody tried to understand it? Which is a very very important topic actually. Yeah.
Yeah, Anirban, I just wanted to ask what will be the percentage of practice non-graded assignments and this coding assignment concepts that you mentioned are also going to be there in the exam. So, how much ratio will be there?
I mean, it's not like that ratio type. The thing is that the professor will try to, of course, test the knowledge on the full course. That's how it is.
Got it. Thank you.
So Anirban, I think it's going to be like that. If there are coding questions, like whatever coding questions are there in the assignments, we should try to perceive them as if they are some sort of numerical or theory. Like the background of it, we must know before appearing in the exam.
Yeah, yeah.
I think that's sufficient.
That's the key. Yeah,
Okay, thank you, Anirban.
yeah. And anything in diffusion, diffusion in terms of E and E theta. So let's try to understand that. So, so the thing was this. So there was the forward process and the reverse process. The forward process was mixing the noise into the image, okay, and denoising is the reverse process. Okay, so you got that one. So, so this is the joint distribution that they write. Okay, and so this joint distribution, as you can see, uh, oh my god. Mm, uh, okay, not able to write somehow. Okay, so this is the joint distribution, okay, of p is x0 to xt, okay, and because this is Markovian in nature, so they can be separated out into terms which are dependent on xt minus 1 is dependent on xt, so they're separated out, okay, in a product form. And this is the pure noise distribution, we know as a normal distribution, 0 1 normal distribution. And we assume that this transition is of the normal distribution form, okay, with mu theta and sigma theta, okay. And so as you can see in this situation, first one I'm not able to write um, thing, okay. It's working. So, so we consider the mean of the normal distribution as this mu theta and sigma theta, and you can see the parameters are xt. Okay, so we are given this version xt version and time at t. Okay, so this is what we are given, and now this is the forward process. We know the forward process already, okay, there is no learning here, okay. So what happens is that we at a fixed noising sequence, we keep adding more noise, okay. So this schedule is determined by beta t, okay, and beta t are defined here, okay. Beta t a small step, okay. So these are defined, okay, and they take it as a like small value and they keep increasing the beta t value, okay. And this is the elbow from the va formulation, you can see that. And this q this q is here, okay. uh, so that's the thing, right? You can write the q xt in the form with respect to x0. So what happens with that is that you don't have to what it means is that given the x0, which is the plane image, okay, you can find a tth time version, okay, and directly we do not have to do it sequentially. So that helps because we know the process exactly. Okay, so there's no point of doing sequentially. Directly is the easier way. So they define the loss function as this, which further simplifies. We will see that. Okay, and qxt minus 1 and qxt minus 1 given xt and x0 is given as this. Okay, this one. So these derivations are there. Okay, so these derivations are there. Further, what you see here is that the reverse process. So the thing, the doubt that has been asked. So now the reverse process comes. Okay, and and for the reverse process, so they are defining the loss function here. Okay, so so you can see the state transitions here, state transition probabilities. So first they define it as a so they define the what do you call that, um, covariance matrix as sigma t square times identity. Okay, so so they do that. Okay, sigma t square is a scalar at a value t at a time t, and then you multiply it with the. So what happens is that you get value sigma t square dot 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 sigma t square, and rest are 0. Okay, so this is what we have here. And so they define sigma t square as beta t once and another time as like this. Okay, so they say that performance is same in both case. Okay, now what happens is that when we compare two two data. Okay, you usually compare the mean of that. Okay, mean is the actual prediction. Okay, so this mu t is the original value you had, is the values of the x0. Okay, and this is the predicted one, so you take the difference of that expected over q, and this gives you the loss function. Okay, and okay, so what happens is that it is for every time step actually. So what it is like, so you're given a image, suppose xt is there. Okay, you denoise it to xt minus 1. Okay, so then you define lt minus 1. Okay, now so they define it like you know that you know the predicted one, that is the xt minus 1 this. Okay, and okay, so the xt minus 1, so they take only the mean of that, which is dependent on xt and x0. Okay, for this, and for so this is the predicted one, and this is the original one. No, this is the predicted one, theta. Anywhere where the coefficient is theta, that is the predicted one. Okay, okay, and this is the original one. Okay, so for every every xt they do it. Okay, and so as you can see, this simplifies to, so when you use the value of the mean here. Okay, from here. Okay, value of the mean, so then this simplifies to in terms of xt, and it goes to in terms of xt. Okay, so it comes into in the form of xt here. Okay, and further what they do, that xt minus 1 can be written in this form. Okay, where z is the 0 1 normal distribution. Okay, after further substitution you get it in the term of epsilon. And so what does epsilon mean here is that so what does it mean, that so you have the noise 0 1 normal distribution, that is epsilon here. Okay, so you sample it in the dimensions of the image. So for each pixel of the image you sample from the 0 1 normal distribution. okay, and uh, and the model predicts uh, another epsilon theta, okay. So what it means is that you are here actually. So this is the original noise, which is 0 1 form. So the what the model predicts has to be also of the 0 1 form, okay. So in spite of matching the images at every step, what we do it one step, we only match the noise that was given and noise that was predicted, okay. So that is the proxy for this, okay. And so with this loss function you can easily train the model. This is the thing for DTPM, okay. So this is the process, okay. The algorithms you can see. So in the training time, as you can see, that they are sampling x0 from the distribution, original data distribution, okay. They are sampling a t from a uniform distribution, okay. How many steps are there in the diffusion? So epsilon is the noise here, and so we minimize this loss, okay, based on epsilon, okay. And here what you have, this xt is here. So the final noisy form that you sample the noise here, okay. And with that you can see that so as you can see, with this you can find, suppose you're given the noise during inference, okay. Given the noise, you can generate the original image, okay. So how? So you take the noise and the time steps are defined, okay. And now what you do, use this formula recursively to get xt minus 1, then xt minus 2, like that to x0, okay. So you get this, okay. Now next what we have here is, so there is another formulation using x, but that was the easier one, okay. We have done that. So this is what is diffusion here. The rest are results and everything. Any doubt? Now we will go into more details and fundamentals of diffusion model, okay. So if you have anything up to this point. Let me switch on the AC. Any more doubt here? I think it's still hard to understand. Many examples doesn't show the details of it. Maybe we can just use the API, like in control net. Show the details of it. What do you mean actually? I cannot understand it. IR. Only three parameters as input. In which equation? What do you mean actually? You can, if you can unmute, then this will be easier. control net. When examples don't show the details of it. Things a little vague if you understand. Mm, okay. So we'll go into more details of it. Okay. And you we use survey paper here.
Oh, hello.
Yeah.
Am I audible?
Yeah.
Hello. Sorry. Yes. It takes only three parameters. The control net library, like the pre whether we are developing a model from scratch, the input and output samples, um, and we just have to
Control net.
provide the mean square loss.
What do you mean by control net?
Uh, it's an diffusion model.
It's a diffusion model. Okay. Let's see. Okay. 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 Yeah. It is there. Yeah. So what here? So it is conditionally diffused. Yeah. So what you're saying here?
Yes, this is the paper part. In the code, actually, if you try to implement it, uh, as in the coding assignments, there are many design of networks. Like we will specify the laws and number of layers and everything. But in case of control net, we just use those APIs and directly. We need not worry about the reverse API. I mean the reverse process
Acha.
at all.
Okay. Okay. Hmm. So that is the
I
achievement
was
of the assignment. What can I do about that? Professor has done it. So, so the assignment is here, right? Practice this one. Huh? Which question?
I mean, it's not an assignment question. In assignment, they have done only forward process, I think. I just checked the some one of the open source code which uses control net, and they have not shown anything in reverse process at all. Uh, I'm not sure where it was. They have just used forward. In forward process, they have used this beta schedule, and then for reverse process, they used MS mean square loss, and they didn't design anything with respect to the loss function with in terms of mu or epsilon. They just a simple neural network. They just called it with eval and
Acha.
um,
Okay. Okay. So they have not shown the full implementation.
correct. Yes. Do we have to worry about it? Since there are many models available online,
Yeah.
they
No.
just
You don't need to worry about it, but going into the details of it helps. Okay. Uh, how things are happening. And they've shown here how is it working in different scenarios.
in the I think it is important in the design aspect of it. If you
Hmm.
okay. Yes.
So that will be beneficial how it exactly works in practice. Okay. Um, okay. So if you look at that, that would be very beneficial. now what we'll go to is so this different loss functions that we show in the paper. So derivations are here. So this is already this already I have shared in the uh, notes section. Okay, and so all you can see. So there is something to learn here. Okay. So as you can see, so first we have seen that the mu form. Okay, the mu form of the loss. This is the one. Okay. Next, what we see, substituting the mean, you can get in the form of x theta and x zero. Okay. So that's another one. Now there will be the epsilon form as well. Okay, but so here is this one, epsilon form. Okay, so these are something to look at actually. So let's try to understand the next part. Okay, therefore you can approximate using mean and everything. Here epsilon theta xt is a neural network that learns to predict the source noise. Okay, so you're just predicting the source noise that determines xt from x0. We have therefore shown that learning a VDM, variational diffusion model, by predicting the original image x0 is equivalent. So the task, actual task is to predict the original image x0. That is equivalent to predict the noise that was added. Okay. Uh, so that's the proxy, easier one to do it. Okay, so you should whenever if you have to code, only use this loss function. Okay, this is good enough. Okay, next to derive the third common interpretation of variational diffusion model, we go to Tweedy's formula. So in Tweedy's formula states the true mean of exponential family of distribution. So the exponential family of distribution is there. Okay, so the mean of that, the true mean, is given. Given samples drawn from it can be estimated by maximum likelihood estimate of the samples, aka empirical mean. Okay, so the true mean is represented by the empirical mean given by the maximum likelihood estimate. Okay, of the distribution. So this is a common knowledge. Okay, so some correction factors is also there involving the score of the estimate. So this is a very important concept to see here, the score of the estimate, they define here. Okay, so in the case of just one observed sample, the empirical mean is just that sample itself. It's commonly used to mitigate sample bias. If observed samples all lie on the one end of the underlying distribution, then the negative score becomes large and corrects the naive maximum likelihood estimate of the samples towards the true mean. So this is the type of the correction. Okay, so what happens is that suppose, so the maximum likelihood estimate estimates around the mean. Okay, but suppose there's too many samples towards the end. Okay, so then the mean gets shifted toward this side. Okay, so 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 the so this correction term subtracts this and shifts the, means the MLE way is the way to know the actual is the way to know the mean. Okay, the true mean you don't know, you're estimating using maximum likelihood estimate and you're subtracting some correction terms. Okay, so that you can make a better estimate. Okay, so that is what they say. And so this correction terms involves the score of the estimate. Okay, this is how we are going through the score based diffusion models. Okay, so mathematically for a Gaussian variable, this 2D's formula states that, so this is the estimate as you can see. So mu z, so this is the Gaussian variable. Okay, and given a z, mu z, estimate of that is z plus summation over z del z log pz. Okay, this is okay. In this we apply to predict the true procedure mean of xt given its samples. Okay, so this is here, we know that. Okay, so this is the one step formula for calculating the noise. Okay, and now by 2D's formula, what we have is that expectation of mu xt at time t. Okay, given xt is xt, so in place of z there will be xt, and the rest is like rest is like this. Okay, so we are summing over z. Okay, so that will be summing over xt. Okay, so summing over xt means just one term. Okay, so that's it. Okay, so according to 2D's formula, the true mean that xt is generated from mu xt under root alpha. So this is the estimate of the, so this is the mu form that we have here. So just replace that actually. Okay, and you get this formula. So they feed it into the mu based plug equation one into the so you plug this into this mu form mu q, and you can get to another form of the loss function, which is given as this. Okay, now s theta, how they define s theta here. So s theta is defined as the neural network predicts the score function. So it predicts the score function, as you can see, and this is called the score function. Okay, this is something important. Okay, in modern papers of diffusion. Okay, so this s theta xt comma t is a neural network that predicts the score function. So you use the score function in place of the noise. Okay, so this del log of pxt is actually a form of the noise only. Okay, so that you can see. So these two terms are off by constant factor that scales with time. The score function measures how to move in the data space to maximize the log probability. Intuitively, since the source noise is added to the natural image to corrupt it, moving it in the opposite direction denoises the image. Okay, so as you're moving in the opposite direction of the noising, so negative is there, that would be the best update to increase the subsequent log probability. Our mathematical proof justifies the intuition. We have explicitly shown that learning to model the score function equivalent to modeling the negative of the source noise. We have therefore derived three equivalent objective to optimize the VDM, learning a neural network to predict the original image x0. So with respect to x0 with source noise epsilon 0. Epsilon 0 and with respect to the score. Okay, score of the image, so they define it as del of log pxt at an arbitrary noise level. Okay, so now we have score based generative models. We have shown that a variational diffusion model can be learned simply by optimizing a neural network s theta xt comma t to predict the score function. This is what we're trying to predict. However, in derivation, the score term arrived from an application 2D's formula. So we'll get into more intuition. So the score function thing is something that we need to go into depth of. Okay, so why optimizing score function makes sense. Okay, we take detour and revisit the energy based models. So we're looking at energy based models now. Okay, so the how they define energy based model. So let's see. So arbitrary flexible probability distribution can be written of the form like this. So this f theta x they define as energy. This y z theta theta actually normalizes it, and you can say this is the probability. Okay, so this is the form of the energy based model. Okay, and where f theta is a arbitrarily flexible parameterizable function called the energy function. This is called energy function. Okay, often modeled by a neural network, and z theta is a normalizing constant to ensure that this is a probability distribution. Okay, so this is another paradigm we are going here. Okay, the move into the energy based models. Okay, now so the one way to learn such distribution is maximum likelihood estimate. However, such this require tractable computing. So how will you do maximum likelihood estimate? So so for MLE you will need to integrate, right? uh, you will do this, not this. So the likelihood function you will integrate. Okay, and for that you do need to compute the normalizing constant, which is this one. Okay, which may not be possible for complex f theta function. Okay, so this integration may not be possible. So one way is to avoid the calculating the normalizing constant is used to have a neural network s theta to learn the score function this. uh, so what they do is that you take derivative, okay, of this formula we've got here already, and so this becomes 0, right? And this becomes minus del x f theta x, right? And this is equals to the score function. Okay, so the score function is equals to minus del x of f theta x. So now what we have here is that we can define the score function as the energy based function. Okay, as a derivative of the energy based function, which can be freely represented as a neural network without involving any normalization constant. So normalization constant is not required here. The score model can be optimized by minimizing the Fisher divergence between the ground truth and the. So what does the score function represent? For every x, taking the derivative of log likelihood with respect to x essentially describes what direction a data space in data space to move in order to further increase its likelihood. Intuitively, the score function defines a vector field over the entire space that data x inhabits, pointing towards the modes. Okay, so what it is doing is that the score function defines a vector field and it points towards the mode. Okay, so it is telling the to to take the prediction towards the mode, so to have a better likelihood. Okay, the score function of the true distribution we can generate by starting at any arbitrary point in the same space and iteratively following the score until a mode is reached. So until the mode is reached we have to move. The sampling procedure is known as Langevin dynamics. Okay, so what we're doing, the plot 6 you can find the visualization of 3 random sampling strategies generated with Langevin dynamics, all starting from the same initialization point for a mixture of Gaussian. The left figure plots this sampling trajectories on a 3-dimensional contour, while the right plots on a ground. Okay, so what you're doing is you're taking samples, okay, and moving step by step towards the mode here. Okay, so that is what is shown here. So this is the iterative movement. Okay, you have, so this is called the sampling procedure, they say, where x0 is randomly sampled from a prior distribution such as uniform, and epsilon is an extra noise term to ensure that the generated samples do not always collapse to a mode, okay, but hover around it for diversity. So what happens is that sometimes when you're when the model collapses, it just for every sample it generates the mode here. So this mode. So this is called a mode collapse. Okay. So that should not happen. Okay. So what happens is that for every sample it will generate the mode. Okay. For that, so that way it doesn't learn anything. So and inference, and during inference it fails. Okay. So that is called the mode collapse. So it does not happen. It should not happen. Okay. And furthermore, because the learned score function is deterministic, sampling with the noise term involved adds stochasticity to the generative process, allowing us to avoid deterministic trajectories. So, adding some noise while sampling, then you can sample multiple trajectories to have the desirable solution. This is particularly useful when sampling initialized from a point that lies between multiple modes. Okay, so which mode to move to? Okay, the visual depiction of Langevin dynamic sampling and the benefits of the noise term is in figure 6. So there are multiple modes here. Okay, and where do you need to converge to? Okay, so that's the question. Okay, so here it converges to this mode, and here it converges to this, little bit here and there, but the mode changes. Okay, so that is the thing they have shown here. Note the objective in equation 157. So 157 we have here relies on having access to ground truth score function, which is unavailable to us for complex distributions such as the such that the one modeling natural images. Okay, so you don't have this score log delta log px. Okay, because this energy function is not known. Okay, and now, so what they say is that fortunately alternatives techniques known as score matching have been derived to minimize the Fisher divergence without knowing the ground truth score, and can be optimized with stochastic gradient descent. So there are some alternative ways to do it. Okay, to uh, minimize the Fisher divergence. Fisher divergence is this. Okay, so this is called the Fisher divergence. And collectively learning to represent a distribution as a score function and using it to generate samples through Markov chain Monte Carlo, such as Langevin dynamics, is known as score-based generative models. Okay, so this is nothing much actually. This is a sampling technique. It's called Markov chain Monte Carlo. Okay, so with this you sample, okay, the points, and then use it for generative modeling. So that is called the score based generative modeling. There are three main problems with vanilla score matching as detailed by Song and Arman. So it is L defined when X lies on low dimensional manifold in a high dimensional space. This can be seen mathematically. All points not point to the okay, so this is the problem you have. Okay, so what they say is that you have a high dimensional surrounding. Okay, and the space is high dimensional, and but X lies on a low dimensional manifold. Okay, so that data that we have at present, the image that we have. Okay, so it lies on a, suppose the thing is that so the data has many dimensions, but the sample that we currently have can be defined only by a few dimensions. Okay, so that is what they say lies on the low dimensional manifold in high dimensional space. This can be seen mathematically. Not all points not on the low dimensional manifold would have probability 0. So the thing is that because it is on low dimension, it feels like there is no change in it at all. Okay, so then so the gradient will be undefined. Okay, the gradient will not be undefined, but it will like basically 0. You'll not be able to optimize. That is the problem we have here. Secondly, the estimated score function trained by Varena score matching will not be accurate in low density regions. This is evident from the objective because okay, something which are rarely seen or unseen samples will not be possible to model. Okay. And some other limitations are there. Okay. uh, so now we move to guidance. Okay. Now what type of image do you want to generate? So that is guidance based diffusion model. Okay. So this is done in the lectures as well, so we go to the lecture notes here. So we move to the guidance lecture materials. So another thing that we covered today is score-based generative models, which are like a improvement over the current diffusion model. They're still diffusion model, but perform better. Okay. Okay. So we need to have some guidance while okay. Okay. It is not taught in the lectures. How is it possible? So this is the one classifier and classifier free diffusion guidance. The video is here. Have you seen this one? Madhuvan? Here it is.
So these X condition things are not taught.
It's not taught.
So classifier guidance was there, but latent diffusion models and these things were not there.
Uh, Latent diffusion model is nothing tough actually. So you're doing diffusion in the latent space of a VA model actually. So let's cover it, okay? So you're saying that the contents of this topic was in this part, huh? Or okay, let's download that as well. Okay. So what we have here is that so we're using guidance here. So unconditional generation diffusion goes from noise to image step by step, not directly suitable to generate desired output. Equal to the stochastic nature generation cannot be controlled. that's the problem we have. Classifier guidance generation. So to perturb the denoising trajectory. How? So let's see that. So train a noisy image classifier P y given x, freeze the classifier and learn the diffusion model. Okay, so what they do is that you have a classifier. So what does classifier do? It predicts the class. Okay, means any neural network supervised model. Okay, so you freeze the classifier and then learn the diffusion model. Okay, so what you're doing is that so this classifier now, after freezing, so it gives guidance here. Okay, as you can see, to the unit. So unit is the backbone of a diffusion model. Okay, so it is an architecture. Okay, and so that is unit here. So this provides the guidance. Okay, the gradient of this is transferred. Okay, as a guidance. Okay, perturb using gradients of the classifier. Okay, so how they perform perturbing, as you can see. So this so you had this epsilon theta. Okay, that should be predicted. So I subtract this one. Okay, and so the gradient of this classifier. Okay, classifier guidance generation. How does it work? To introduce a class conditioning, the probability becomes conditional probability. This that is. So this is conditioned on the class now. Okay, previously it wasn't. Okay, now so using Bayes theorem, the new score function for the diffusion models become so the new score function. so this becomes the this is what we need here. Okay, and using Bayes theorem, as you can see, this can be written as the standard diffusion model score and the score for the additional conditional generation. Okay, so this we have here, classifier guidance generation. How does it work? So gamma is the guidance scale, how much guidance do you need. Okay, and revert the gradient and the logarithm operator to see what's going on. So it is something like this, and raising the conditional distribution term, so raising the gamma to the power of so it raises the temperature of the distribution, where gamma is the inverse temperature parameter. So that is how they define it. Classifier guidance thus enables us to apply the temperature tuning selective to the segment of the distribution that reflects the impact of the conditioning signal. So it is applying specifically to that part of the distribution which impacts the generation of the specific image. Okay, so this is the loss function we have here. So classifier guided, we are doing it. So this is the diffusion model which predicts the noise. Okay, so this is a reverse process, and this is the classifier we have. And so this is it. Okay, class label y, gradient scale s. Okay, so new epsilon. So the new epsilon, the noise that 0 normal distribution is this one. Okay, the predicted one, and the another coming from the classifier. When you are not using classifier guidance, so the images are like this. Now you're using classifier guidance, then what? You can produce a specific image, as you can see. So here you can see cat, dog, and everything is there. Humans are also there, but here only dogs are there. Okay, so that's the benefit. Classifier guidance requires a dedicated classifier specifically for guidance. Classifier used for guidance also need to tackle high noise level to provide a useful signal. How to get class guidance without an independent classifier? So they basically want a unsupervised technique. Okay, because the supervised technique, as you can see, you need a trained classifier already. Okay, and on a supervised data, which is a little challenging. So use the diffusion model itself for guidance. Okay, so this is the classifier model that we have seen. Okay, you can use the Bayes rule here, provided the logarithm, then you can get something like this, and then we can take the derivative over it, okay, over xt, and so it is not dependent, so it becomes 0. This is what we have here. So this is a classifier model. This is the class conditioned score function, and this is the original score function. A few slides ago we had so we had this one, right? So what we can see here, that so except the gamma term, basically it is the same thing, right? So so we substitute it. Okay, so first we've got this one, okay, and this is also known. So they substitute the del log py given xt, this one, okay, and okay, so you do that one, this one, okay, is substituted into this, okay, and what you have is this so this conditional score and unconditional score is here, okay. This is the conditional score, this is unconditional score, okay. So it can be written as unconditional score and conditional score and unconditional score, some subtraction of that. Same neural network can generate both conditional and unconditional scores. That is what they write. So let's understand that. Same neural network, na? So how we have approached the problem, let's see that. So here we don't want this one, right? Because it's the classifier one, okay? And we don't want the classifier, so we substitute that, okay? So that's easy to understand here. And now so this is the conditioned one, okay, and this is the conditioned distribution, and this is the unconditioned one, okay. And now what we have here is that the diffusion model earlier was learning the unconditioned distribution. Now we say that so the score is given here, okay. So here we did not need to use the classifier first of all, okay. So that was substituted, and so here we'll have to go through the energy based route, okay. So then you can, from the same neural network, you can get the both conditional score and unconditional score to model the generation. So use the diffusion model to get perturbation for the guidance. Trained a conditioned model with conditioned diffusion model with conditional dropouts, where conditioning information y is removed to make the model unconditional. In practice, it is often replaced with a special input value representing the absence of the conditioning information. Achha. So they specifically trained a conditioned model, okay, and when it is not required, you need unconditional, then you just remove the conditioning term. Both conditioned and unconditioned diffusion model can be learned via a single neural network, okay. So the thing is here. So require P unconditional, provide unconditional training. So repeat what they're doing. Say sample the condition and the x value. So if C is phi here, then it is unconditioned. Okay. lambda from it, then epsilon, and then you define z, then take the gradient step here, and until it converges. Okay, so as you can see, first it was random, now it is conditioned to produce faces of dogs. Classifier guidance seems to work better than classifier free guidance. Okay, because you are using a lot lower gamma. Classifier from the generative model itself. Generative model gradients are much more robust. Okay, so these are the things. Next, so classifier guidance, we've got it. Okay, next is this one. So the text condition generation. Okay, so we're conditioning on text, not on class. Okay, so this different types of conditioning are there. Another is like slot conditioning is there. Okay, so but that is not in the syllabus. Okay, so slots are defined as some data type which are again are used for conditioning diffusion models. Okay, so in the last lecture we saw the classifier and classifier free guidance. Okay, so the additional input label to condition this distribution, so we can leverage existing language or vision language model instead of a classifier. Okay, so how to do it? So we already have class based guidance, now we need text based guidance. Okay, so this is a sentence given and you have to generate the image. Okay, so this is a glide for OpenAI, propose the caption and clip guidance for the text. So this is the thing we have. So this is our diffusion model here. Okay, and now the caption is there. This caption, the image needs to be according to the caption, so it goes to the clip text encoder. So the clip is a contrastive learning method. Okay, where the image, and so the model learns to pair the image to the caption. Okay, so if you have the trained encoder of that, if you put the caption, it knows which image to generate. Okay, so from text caption, you put it into this text embedding, it's given to it, and then it helps to generate. Okay, so they use a pre-trained model clip. Okay, which is a very big model. Okay, so it has all the knowledge. They pair the caption with the images. Okay, so given a caption, it always know which type of image to generate. Okay, so okay, can you give examples of using unconditional training? Using unconditional, the DDPM that we have seen is unconditional training. Actually, there was no conditioning there. Conditioning is required to generate the image of our specific needs. Okay, so that is what we're seeing. The first was classifier guidance. Use a classifier model for separately trained classifier model is used to provide classifier guidance. Another is that you train it in a conditioned way. Okay, when you need unconditioned score, you just input phi a empty token into it for unconditional generation. Okay, so you get both conditioned and unconditioned score, so that are used in the loss function for generation. Now next we see is the text guidance. Okay, that was first that we had was class guidance, now it is text guidance. Okay, so that is what we are seeing. So this is the, so first they explain the clip model. Okay, so here what you have is that you have a text encoder which is not trained when you're modeling it. An image encoder is also there, so you can have CNN or VIT. Okay, here text encoder can be like GPT type. Okay, autoregressive. Okay, now they the embeddings that are provided here. Okay, this is the embeddings that you get from it. Okay, so these are matched using a contrastive manner. Okay, so you can understand so whichever is more related will be made closer, and which is not related will be distant further. Okay, so they use a contrastive objective. Okay, and we'll see more of it in later. Okay, now clip guidance. Okay, type of guidance they use? So they use the clip similarity score. Okay. So FXT is defined as the clip image encoder and GC is the clip text encoder here. Okay, so first things to understand. S is the guidance weight, same as gamma here. Okay, and and this is the covariance matrix. Okay, so what you have here is that so GC is the text encoder, right? And this is the image encoder. So we are defining a new mean here with respect to the so the C is here. C is the prompt they define the caption. Okay. So conditioned on the prompt, you need a new generation with the mean mu theta. Okay. So here what you see, the old one. Okay, and so this is the conditioning. Okay, this is the parameter S. Okay, and this is the covariance matrix here, and this is derivative with respect to xt. Okay, of this quantity they're doing. Okay, so this is the new mean they've got. Okay, so but they see that without retraining the clip. Okay, so clip is a pre-trained model. Okay, so without retraining the performance is not so good. Okay, so classifier free guidance with caption conditioning. So they're using only caption conditioning, not using class. Okay, so this is what you have here. Okay, okay. So it was similar to the previous one. So the classifier free guide. So let's see that. So so we are not using a classifier. Okay, so this was previous one actually. Classifier free guidance with caption conditioning is still there. Okay, so that is how they define. Now clip guided diffusion guidance. Okay, so with clip this is the form. Okay, now okay, so this was the with pre-trained clip encoder how they did it. Okay, now the scene total changes. Now we move towards pixels. So what we have seen up to this point are pixel level diffusion models. Okay, so unlike VAE, you don't reduce the space of the diffusion model. So the image size, whatever that is, it is same as image size is same as, I mean the latent states that you have, they have the same dimension as the image. Okay, so that we have. Okay, so what it means is that it is quite computation expensive, very slow process, so many iterations, but on the original space. Okay, so this is the problem here. Network parameter count larger, so significant computation power, longer to train, GPU memory, very slow at inference. Okay, the problem we have. So how can we reduce the computation cost? So we move towards latent diffusion models. So what it means is that we're training the diffusion models inside the latent space of a VAE. Okay. This is a faster and everything benefit you can see. So VQ VAE is one type of VAE model used to model the latent space in which the diffusion model trains. Okay, so the encoder takes image X and so encodes in a lower dimension ZE. Okay, so VQ layer. So as you can see, the CNN encoder we have here, and so this is the embedding space in which the diffusion happens. Okay, and then it is regenerated into the original space. Okay, and so as you can see, the VQ takes ZE samples embedding from a dictionary based on the distance del ZL to output ZQ. Decoder network takes ZQ and output X test to create X. Okay, so that's simple enough. So what we are happening is that we are using diffusion in the latent space of the variation autoencoder. Simple enough. Okay. loss function will have loss function of both. Okay, so this is the what is SG here? So this is the reconstruction loss. Okay, so reconstruction loss means the image that from the latent to the original we reconstructed. So embedding space loss, a dictionary learning algorithm that uses L2 error to move the embedding vectors EI towards the encoder output. Okay, so what it is doing is that so SG represents stop gradient. Okay, so what it means is that so what does SG here represents the this because the ZE, the forward process, does not have any parameter to differentiate, so we are not differentiating that. So SG represents that here. Okay, this is E is the uh, so it is moving the towards the encoder output. Okay, so encoder output. Uh, so what we get here is that this is the diffusion process. Okay, very noisy form, then denoise it. Okay, so it moves towards this towards the noisy form. Okay, so you're actually predicting the noise here, and here what we see is that this is the commitment loss. It is used to control the volume of the embedding space and make sure the encoder commits to an embedding. So what does this mean? This I am not totally sure what is commitment loss here. Volume of the embedding space, they say. This is something to see. Okay, I'm not too sure. To achieve LDM, first compress the image using VQVAE encoder epsilon to lower dimension latent embedding. Z is fed into unit model to learn to generate latents. Okay. Okay, so we are using this loss function. This is it actually. So we will finish it up here. Any doubt? So next session there will be an extra session. Okay, so we will cover the week 12 there. Okay, and that will be it. Okay, so that will focus on fundamental self-supervised learning in images in vision. Okay, so that will cover that one. Okay, any doubt here? So what you learned today, the DTPM we have revised, and after that we have seen the score based generative models. What is the meaning of score? Okay, next is the different types of guidance. One was class based guidance, and was the classifier free guidance when the class is generated inside the diffusion model only, with the diffusion model only. And there was the text based guidance, and then the last we had was the latent space diffusion models. Okay, these are the things we covered. Any doubt? No doubt. We'll finish it off here. Okay, thank you very much. Okay, should we need to run Python in exam? Most probably not. No, there will be very simple question. There might be very simple question just to understand your understanding of PyTorch library. That is what professor has told me. Okay, so it maybe there like code is given and you need to understand something or something. Conceptual question or code based question. Only conceptual questions will be there. There may be one or two coding questions, but you don't have to mostly code. It will be very simple actually, and just for to test your whether you have done some coding or not. That's it. So nothing to worry about on coding questions. coding questions mostly will not come. Okay, any other doubt? I assume that from what you've seen, score pay function is considered to be along with MSc laws. Score function is to be considered along with MSc laws. Yeah, score function is considered because we have seen that in more general models, the epsilon noise based form doesn't work actually. So we have to move to score based model, and due to the energy based formulation, we have that benefit. So the score based structure is usually followed for all the modern models. Yes, and the MSc loss is always there. Okay, so we have so in the survey paper I've shared, they derive the all the reconstruction KL divergence form. It simplifies to a squared error form. Okay, so the squared error loss is the main loss in diffusion. Anything else?
So I have one question, sir. Like, is that possible to give the class and text at the same time? Because there are two types: classifier free and with text conditioned diffusion model. So if I want to put both, is it possible?
Classifier and text guidance both, but you don't need two type of guidance, right, Nina? uh, so the thing is that you need to produce conditioned images. Okay, and if you can do it with one method, why do you apply it? Because both are serving the same purpose, right? So you just use the class based one or the text based one. Okay.
Okay. No, but the thing is, what is the advantage of text over class?
I mean, the thing is that suppose you give a prompt in GPT, I want a picture of a dog. So it is not you're not specifying a class, right? You're giving a prompt, a caption. This caption is taken into the clip encoder, and this clip encoder produces the embedding that is put into the diffusion model to produce the conditioned image.
Okay.
You don't exactly have a class, right? You have a text
Because
based.
I found some diffusion model wherein I can upload an image,
Hmm.
and then also I can give the prompt at the same time. So I thought like it is kind of hybrid of both. So how it is working behind the scene?
Um, so what you're saying that you are so in diffusion when you have to generate, you are giving a caption or you are giving a class,
No,
right?
I am uploading the image. Also, I am giving the text prompt.
But why do you need to upload? You need to generate the image, no?
Yeah, yeah. Means I may have to edit the image also. Like I can select a certain part of the image. I want to replace it with uploaded image, and I can also say that what changes I want in the
So
edited image.
what it may do it that you have a caption, you have an image. Both are so image is passed to the image encoder of the clip model, and the text is passed to the text encoder of the clip model. So both embeddings are now fed into the diffusion model for guidance in that case.
So is it kind of hybrid of this classifier and text condition?
But the image that you are embedding that you're using is not a class, right? For class conditioning, what you have is the diffusion model is trained from the scratch with class guidance. Okay, or you use a pre-trained classifier model. Means a pre-trained, a separately trained classifier model. Classifier model you understand, right? Suppose what it means is that you have a image corpus, a labeled image data, and you are making a model so that the model can predict in inference which class a specific image comes from. Okay, so this is called the uh, uh, so what is this called? This is a classifier model. So it learns to classify which class a specific image belongs to.
Okay.
So when you're inputting getting an image. Okay, so what it does, should does do is make an embedding of the image and then use it for conditioning.
So in the end, what we are feeding to model is the embeddings in the form of text and the image. Is it
Yeah, yes, yes.
combination of both? Okay, got it. Thank you.
Okay, welcome. So is it done now? Any more doubt? No doubt, right? So I'm closing this off now.